Hi. In this video, I'm going to discuss function generation using a four-bar mechanism. In particular, I will be discussing precision point synthesis. I will not be discussing least square method or any other method that you may think of, optimization, etc. I will be simply considering precision point synthesis, but I will be discussing 3 precision points, 4 precision, and 5 precision point synthesis. Let me share my screen first. I will be showing everything using Excel, not present a PowerPoint. A four-bar mechanism as shown, consisting of 4 links, including the fixed link. Link 2 is the input, link 4 is the output, link 3 is what we call coupler link. There's a relation between the input crank angle theta and output rocker angle or output link angle phi. And this relation is given by what we call Freudenstein's equation, which was first given by Freudenstein in 1953 and 54. Basically, it is a very simple equation, K1 cosine phi minus K2 cosine theta plus K3 is equal to cosine phi minus theta, where K1, K2, K3 are related with the link lengths as shown. K1 is equal to A1 over A2, K2 is equal to A1 over A4, and K3 is equal to A1 squared, A2 squared minus A3 squared plus A4 squared divided by 2A4, A2. If you have determined K1, K2, K3, the inverse or the link lengths can be obtained from these equations. Notice when you are correlating the crank angles, if you are not concerned with the size of the coupler, with the size the coupler of the curve traced by the coupler curve, etc. If it is the angular relationship that you are concerned, the size of the four-bar mechanism does not matter. You can increase the size tenfold or reduce it to tenfold. The angular relationship will remain the same. So in this case, you can select any one of the link lengths arbitrarily. It is the ratio of the link lengths that is important. Now, if you are to correlate crank angles, you can select 3 correlated angles, for example, theta 1, phi 1, theta 2, phi 2, theta 3, phi 3, 3 crank angles to be correlated. In this case, you will write Freudenstein's equation for these 3 angular correlations. This will give you 3 linear equations in terms of K1, K2, K3, because you will be defining phi and theta in those 3 equations. If the coefficient matrix is not equal to 0, you are going to have a unique solution for K1, K2, K3. But this does not necessarily mean you are going to have a good, feasible four-bar mechanism. Number one, K3, in terms of these equations, notice A3 can turn out to be imaginary, in which case this mechanism does not exist. Or you have defined these 3 positions. The four-bar mechanism for this crank angle can be assembled in 2 different forms. This form we call open form. If this link is in a cross form, we call it cross form of the four-bar. It is possible that one of the positions that we have specified can lie in the second bracket, in a cross form or an open form. So not all 3 positions may lie in the same form of the four-bar mechanism. In that case, it is useless. That's not a feasible four-bar. Or in certain cases, the link length ratios can be such that one of the links, as A1 is equal to 1, one of the links can turn out to be very small or very large. And that is not possible. Or the transmission angle can be very bad. So you have to check your result in all cases. Now, this is the correlation of crank angles. In this case, you have three parameters, notice, K1, K2, K3, or the ratio of the link lengths, three parameters. However, you can select theta initial and phi initial if you like. If you are going to generate a function y is equal to y f of x, in between x initial and x final, you have a certain delta x value. Corresponding to this delta x, using y equals f of x, you will determine delta y, which may be, if the function is monotonic, it will be y final minus y initial. Or if the function is, there's a maximum or a minimum in between the function, it will be y max minus y min. It will be delta y. Now, what you can do is, you can select any initial crank angle that you like, theta initial, phi initial. You can select del theta, del phi, the range for the crank angle, crank rotations. This depends mainly on the problem that you are going to solve. Usually, it has to be, you would like to have it as large as possible, but Ferdinand and others have shown that if it is greater than 120 degrees, you may not end up with a feasible solution. So try to keep it within less than 120 degrees or so. In that case, once you define del theta, del phi, you can define scale factors, what we call scale factors, k phi, k theta, del phi by del y, del theta by del x. And you will have one-to-one relation between x and theta, y and phi, as shown. Notice theta initial and phi initial will be also arbitrary, so you may use these as design variables. In that case, you are going to end up with 5 design variables instead of 3 design variables, which are the link lengths. What we shall do is we shall start with three precision points using the link lengths as design variables, and later I'll add the theta initial and phi initial as design variables. Now, you can select any 3 points within 3 values of x within this range. And you will have these points, at these points, you are going to have 0 error. But within the range, between x initial and for x final, the required function and the generate function is going to be different. And there will be some error involved, which I will call epsilon. These precision points is arbitrary. You can select it anywhere you like. However, it was Chebyshev who said the maximum error within this range will be minimum if the maximum error within this range will be minimum if the maximum and minimum errors within this range are all equal to each other. Meaning that these maximum and minimums are all, if the absolute values are all equal to each other, then the maximum error will be minimized. And he has found a polynomial set, which is known as Chebyshev polynomials, which satisfies this condition. And for those polynomials, the precision points, the points at which error is 0, is given by what we call Chebyshev spacing. For n precision points, the equation is as shown. For example, if n is equal to 3, it will be 1/2 x final plus x initial minus 1/2 x final minus x initial cosine 2j minus 1 over 6 pi for j equals 1, 2, 3. It has been found. By the way, Chebyshev has found these using for the mechanisms, in fact. But it is a general mathematical rule which has been used for all other, in all other fields. Now, if you don't know where to select your these precision points, it is advisable to use Chebyshev spacing and determine xj using this equation because from practice we know it is better than selecting equally spaced data or any other form. Now, what I will do is I will give an example for the synthesis. First of all, let us start with 3 precision point synthesis. I will solve y equals log x for x in between 1 and 10. And I will select delta theta under 20 degrees, delta phi 60 degrees, and I will select A1 equal to 1. And initially, I will select theta initial 45 degrees, phi initial 65 degrees. Del theta, del y will be equal to, del phi will be under 60 degrees. Del x will be equal to 9, as you can see, 10 minus 1, 9. Del y, log of 1 is 0. Log of 10 is, log of 10 is equal to 1, I know, but let me show it. So del theta by del x will be equal to del theta by del x will be the scale factor for theta. It is so many degrees per unit change in x, and del phi by del y will be equal to 60 degrees per unit change in y, degrees per unit change in x. Okay? Now I'm going to use Chebyshev spacing, so let me move this formula over here. I could have, I can write it over there, but no problem, so that we can see. X will be, for 1, it will be equal to 10 plus 1 over 2. It is 11 over 2 minus 10 minus 1, 9 over 2 divided by 2 times, open up parentheses, cosine of, open up parentheses, j is equal to 1, 2 minus 1 is 1, divided by 2 times 3, I'm using 3 precision points, 6. So it is equal to pi, this is how I write pi, over 6. Let me copy these. It is for j is equal to 2. Notice the first term does not change. The 9 over 2 does not change. Cosine, now j is equal to 2, 4 minus 1, 3 pi over 6. It is pi over 2. Okay? And for j is equal to 3, 5 pi over 6, as you can see. 5 times pi over 6. These are the 3 precision points at which there will be no error. Then the y will be equal to logarithm of 1.6. By the way, you see 1 digit in here. Actually, Excel performs all these operations in 16 digits. So you will see whatever you want to say. Okay, like this. If you want, you can say all the 16 digits, but I believe you can say that it's not necessary. So let me decrease the size of these cells so that we see reasonable amount, not all. Theta, remember this formula? Theta initial plus k phi, x minus x initial. It will be like this. Is equal to theta initial. I'm going to copy this formula downward. So I would like to keep theta initial will be for all those cases. So I will type F4. You'll see the dollar sign. This will fix that cell. Okay. Plus k phi theta, again F4, times x value minus, I'm not replacing I'm not fixing that cell, notice, minus 1. X initial. Do it like this. Notice, what is it? Theta initial plus k theta. X is this value minus x initial 1. This value, again, correct formula. Phi is equal to phi initial F4 plus k phi F4. Since y initial is equal to 0 times y. Let me repeat. The reason I'm not putting a parentheses and say y minus y initial, because y initial is 0. That's why I notice these values will not change as I move this formula to another cell. I'm making them fixed. Those are fixed. Let me repeat. If you extend these, you may see more terms, 16 digits, more digits as well. Now, in my formulas, I'm going to use radians. These are in degrees. In my formulas, I'm going to use radians. So let me convert all these to radians. What I can do is that value of in degrees times pi, this is how I write pi, divided by 180. But instead, what I will do is, I have already done it, I have written pi over 180 degrees over here. And, and I have given it a name, D-R, degree to radian conversion unit. Now, in that case, rather than writing it pi over 180 times D-R. This seems to be much simpler because I will be using that dr over and over, as you will see later. Copy them like this, move these cells. Notice this is phi 3 times dr. So I have these terms. Now, here I have the equation for the 4-bar. Let me write these the coefficients like this. Cosine phi 1 is equal to cosine of phi 1 minus cosine of theta 1 1, and then the column vector cosine of phi minus O. The reason is you have to place an equal sign if you are going to insert a function. Otherwise, it would take it as a literal. Cosine phi minus theta. Once you have entered these, you can copy them like this. This is a relative cell addressing. Notice this is, as you pull it down, the reference will also be pulled down. And then these values will be 1 and 1. This is your coefficient matrix. This is your column vector. Now what you have to do is solve for K1, K2, K3. In linear algebra, K1, K2, K3 will be equal to inverse of the coefficient matrix times the column vector will give you the result. Okay, Excel has those two operations. First, let me show it like this. The inverse matrix is going to be 3 by 3. So formulas, insert, math trick, go down to M matrix. M inverse returns the inverse matrix for the matrix stored in an array. Click. The inverse matrix must be the inverse of this matrix involved. Click OK. This is your inverse. Come over here, mark these 3 cells. Now, again, go to the formula. Again, go to M. M inverse, M determinant, M mult. M mult. You are going to multiply this matrix with this column vector. Correct? These are the values for K1, K2, K3. Let me copy these as follows. Control C. But over here, I will say paste special. I will copy the values only, not the formulas. Because here I have the formula. Here I don't have the formula. I only have the numbers to show you something. I will erase this, and I will erase this value. If you get familiar with the operations, you can write this formula as follows. Equal to M mult, multiply the matrix, open up parentheses, M inverse, take the inverse of this vector, this matrix, close parentheses, comma. In some computer settings, Excel settings, it may be semicolon. Let me remind you that. Open up parentheses, this column vector. As you can see, you obtain the same result. So I will erase this. Now, once you obtain K1, K2, K3, now you can use inverse these equations. Let me pull these down over here so that you can see. A1, I'll take it as unity. A2 will be equal to A1 divided by K1. A3, I will do it later because A3 involves A4, is equal to A1 over K2. A3 is equal to SQRT square root, open up parentheses, 1 squared plus A2 squared plus A4, I hope I can get it, squared minus 2 times K3 times A2 times A4, close the parentheses. Now, A2 and A4 turned out to be negative. In this case, if theta initial is 45 degrees, you see the length cannot be negative. It is it turns out to be negative, if the result turns out to be negative, it means you have to measure this angle not from this side, but from the other side. This revolute joint will be on the other side. So you have to add 180 degrees to theta initial. That's what it means. So what I will do is, I will select minus, make it a positive. But I have to know that it is negative initially. Otherwise, make it positive. I have to analyze this mechanism. I have to analyze now. Now, normally, for the analysis, I can, write the formulas, etc., and perform this analysis. But I have a simple choice, and that is I have written small function routines. If you go to the developer menu and turn on Excel sheet, there are no macros involved in this case right now in this instance. You can download this a file known as basic bus file. It's very simple. And now you have it as a module over here. You have simple function routines. I'm not going to discuss these. It is simple function routines that will solve a 4-bar as if it's a cosine function or something like that over here. You have 4-bar, which gives you the output link angle even when the input link is given. You have 4-bar coupler, which will give you the coupler angle when the input link angle is given. 4-bar 2 gives you both coupler link angle and output link angle at the same time, as you can see. There are transmission angle, 4-bar TA will give you the transmission angle. So for the slider crank, etc., you have all those formulas. I'm not going to discuss that. It's another topic. But in here, I will be using 4-bar function. And the way it is like this. I have to analyze the mechanism. X is in between 1 and 10. So what I will do is, first of all, I will select X1. I'm going to select 0.5 increments, but if you want, you can select 0.1 increment or 0.2 increment or 0.01 increment. This depends on the accuracy you want to solve. But right now, I think 0.5 is good enough. Otherwise, the length of the array that I'm going to form will be quite big, large, but it is the same effort, I will say. As you can see, I can pull this down to 10. Now I have 21 value for X that I have to determine. Next, I have to determine the Y required. This is the Y value for Y required, log of X. Notice, go to the bottom right corner of the cell, double click, you will obtain all these results. Theta, I have this formula, is equal to, now, since this is negative, I will add 180 degrees to theta initial, is equal to theta initial, I'll press F4, plus 180, I'm doing it in radians, in degrees, sorry, plus K5, again F4, times open up parentheses, x minus x initial, press F4. Again, double click, you will end up with the theta values. Phi is going to be generated with the 4 bar using these crank angles. Right now, if you don't, you may not. Later, you can type in the formula as if it's a cosine, but go to the formulas menu, insert function. Besides method trick functions, you will see user-defined functions, and you have all these functions user-defined. As you can see, returns the rocker angle with respect to the fixed length when the link length and the input crank angle is given. Config is equal to 1 if the 4 bar is assembled in open form, or minus 1 if assembled in cross form. Angles are in radians. Okay? Click OK. It asks you, what is the crank length? Notice I'm taking positive values. What is the coupler length? I'm pressing F4 since I want to make those link lengths fixed. What is the rocker length? Press F4. What is the fixed length? 1. Press F4. Config, first I will take it as 1. Later, if I see that it is not 1, if it's not open form, I may change it to cross form. Theta is equal to this angle, but it has to be in radians, times d-r. Remember d-r? Conversion from degrees to radians. That's it. Let me change that into degrees is equal to this value divided by d-r. 150 degrees. But this angle must be in the opposite direction, so I have to subtract 180 degrees from it. Notice there's a huge difference. This is minus 30 degrees, whereas 65 degrees. So there's something wrong, which means your 4 bar mechanism is not in open form, but it is a cross form, in a cross form. So take it as minus 1. This is close. There's an error, 70.5 degree error between theta initial and phi initial and this angle, but it is good enough. This is the result. Y generated will be, I will again use this formula, but this time Y initial is 0. Sorry. Y will be equal to 1 over K phi minus phi initial. So Y generated will be equal to 1 over K phi x times, open up parentheses, this angle, 72.49 minus 65 degrees, press F4. Meaning, fix that F4 because it's going to be the same for all the remaining values. This is the Y generated. The error involved will be the difference between Y required, minus Y generated. That's the error. Now, let me plot these. I will move these over here so that I will have some space. I don't need it. Let me first insert chart. smooth curve. Excel thinks that it's clever and it gives you some select data. You remove all these, add X values, Control Shift, down arrow, Y values. I will do it like this. Not bad. As you can see, error is 0 at the points that I have defined, and it changes format axis. I will make it starting from 1, going into 10. Okay, every 2 units is good enough. That's it. Let me see what is the maximum error. Epsilon max, epsilon min. First I write it like this. Then mark E instead of times 0, make it symbol, and mark max, make it subscript. Do it like this, and then change it to IN. If it is too small, is equal to max, open up parentheses, from here to here. Min is equal to min, open up parentheses, from here to here. So it is 0.25 units. It's quite big because Y is changing between 0 and 1, and you have 0.25 error. That's huge error, as you can see, right? This is 3-point synthesis. I have selected 3 precision points. Now what I'm going to do is, what if I use theta initial or phi initial as an initial guess? What I will do is, first let me rename this cell. 3 precision points. That sheet is named as 3 precision points. Okay. Now what I will do is move or copy, create a copy of this sheet. Here I have a new sheet, the same way. Rename it as 4 precision points. This is 3 precision points. The previous case was 3 precision points. Now what I will do is, I will assume theta initial is a design variable. Theta initial can be any value you like. Number 1, n is equal to 4. I have to change these points. So what I will do is insert a line. So I'm going to write in a new equation. I'll select another precision point, insert over here, so that I will have these lines. Okay. Now my equation will be x initial plus x final will be the same, 9/2, but n is equal to 4, 8, 2 minus 1, 2 minus 1, 1, pi over 8 is my first precision point. My second precision point is not going to be, it will be 3 times pi over 8 My third precision point will be 5 times pi over 8. And my last precision point, which is not in here, oh, sorry. I will copy it like this. 7 pi over 8. Y will be okay. Now I'm going to write another equation. Then I will do like this. Move it down. 1. Move this down. Now, K1, K2, K3 that I have obtained is using the first 3 equations, not all the 4. Using the first 3 equations, I have obtained this K1, K2, K3. However, I had to satisfy these 4 equations. I can only have a solution for K1, K2, K3, provided that the determinant of the augmented matrix is equal to 0, meaning the rank of this four equations in 3 unknowns, the rank must be equal to 3. What is the augmented matrix? It is the sole 4x4 matrix. Determinant will be equal to, if you want, you can check M returns the matrix determinant of an array, open up parentheses, take this. Now, these 4 equations in 3 unknowns, K1, K2, K3, can only have a solution provided that this determinant is equal to 0, but it is not. If this determinant can be made equal to 0, then you have a solution for K1, the solution for K1, K2, K3 will be these values. So what I do is this. Go to the data solver, reset all. Let me first reset all. Well, it is almost reset. I want to make this value equal to 0. By changing cell, I'm going to use phi initial as my design variable. Make this cell equal to 0 by changing phi initial. That's it. You can use 2 algorithms. One is GRG nonlinear. It is a gradient. It's a gradient method. Or you can use evolutionary, which is, from the name itself, it is a heuristic method, evolutionary tool. I prefer, if possible, I prefer GRG nonlinear because it's faster. If I cannot find a solution using, if GRG nonlinear diverges or something happens, then I would try evolutionary. Now I'm going to use GRG nonlinear. Oh. Voila, 10 to the minus 9, which as far as I'm concerned, it is 0. Correct. This is the solution. Now, all these 4 equations are satisfied with phi initial equals 115.7 degrees. Let me repeat, there are more digits involved, but I don't care. Now, notice what happens. The link lengths are all positive. I have to change all my analysis. First of all, these are the same. I'm not going to add 180 degrees to theta angle. Theta initial plus that value will be good enough. Correct? And let me do this for all angles. Now, phi 4-bar function, notice in the previous case, I have used these cells as A2, A4. Now I have to move this cell over here, move this cell over here. I'm taking positive values for the link lengths. Again, double click so that it changes all those other values, a change. And lastly, I have a subtract 180 degrees. Don't subtract 180 degrees because it is positive. This is the link length that you're going to measure. Voila. As you can see, this is the curve. Now, if you look at the error, the maximum error is 0.01. Compared to 3 precision point synthesis, which was 0.25, it is a huge improvement. In fact, what you can do is, by moving this precision point closer to 1, you may decrease this value, and you can move these precision points. There's a method known as Freudenstein's respacing formula. I'm not going to discuss that, with which you can decrease, you can make those errors equal. But even with simple Chebyshev spacing, you can see that you have decreased the error tenfold, more than tenfold, by the way. And it is interesting to note that the number of precision points, 1, 2, 3, 4, 5. So you have an extra bonus in this case. Now, if I want to, this is 4 precision points. As you can see, this is very easily, I can move to 4 precision points. Now, if you want to move to 5 precision points, let me again take 3 precision point synthesis. Move or copy, create a copy. I have created a copy, and I'll rename it as 5 precision points. Such, okay? And what I will do is, first of all, I'll insert more lines, more rows, so that I can write those 5 equations. Insert. Now, look, I have n is equal to 5. 2 by n is 10. So pi over 10 will be my first precision point. The second precision point is 3 times pi over 10. You can check. The third is 5 times pi over 10. 2 more. 7 times pi over 10. 9 times pi over 10. This is the beauty in Excel. All you have to do is move these cells. Due to the relative cell addressing, you can do this very easily. Now, I'm not moving 1, because if I move 1, it will be 1, 2, 3. So don't do that. Now I have 5 equations. However, I have obtained K1, K2, K3 from the first 3 equations. What I will do is, the rank must be equal to 3. The rank of the matrix, the rank of the system of equations must be equal to 3 in order to have a solution for K1, K2, K3. So I have 5 equations. So any 4x4 augmented matrix that I have formed must be equal to 0. It is sufficient to have 2 of those equal to 0. So what I will do is, this time that 1, that 2, equal to m determinant open up parentheses. Notice the first 4 equations. Let me see. I'm doing this the first time. If I move it like this, it is the first equation is not involved. It is the last 4 equations. Now these two are not equal to 0. I have to make it equal to 0 so that K1, K2, K3 is a solution. What I can do is I will take the square root of determinant 1 squared plus determinant 2 squared, like that. The only possibility for determinant 1, determinant 2, when this value is equal to 0, since it is positive definite, when this cell is equal to 0, both determinant 1 and determinant 2 will be equal to 0, as you can see. So it is sufficient to have this value equal to 0, in which case you are going to have the rank of the matrix will be equal to 3, and this K1, K2, K3 that you have obtained from the first 3 equations is a valid solution for 5 precision points. So what I do is go to the data again, solver tool. Now make this cell equal to 0 by changing both of these values. Okay? Usually I would add 2 constraints. In the previous case, I haven't added, but it's preferable to add. Make this cell 1, especially if you are using evolutionary, you have to do this. Because it has to be in between 0 and 360 degrees. Add, any angle has to be equal to, any angle is a variable that must be in between 0 and 360 degrees. So, let me read. Make unconstrained variables non-negative. So in that case, theta initial and phi initial would be in between 0 and 360. I'm not bounding anything, but I'm specifying it in terms of mathematics. Now, I'm still going to use GRG nonlinear. Solve. Voila. 10 to the minus 8 is a good solution. 10 to the minus 9, 10 to the minus 8 is a good solution. Now, again, these values are positive. Let me do what I have done previously, or in this case as well. Eliminate theta initial, because I'm not going to measure it from the opposite side. I'm going to measure it from the theta as before. Move these. Eliminate 180 degrees. Voila. Now, the maximum error is 10 to the minus 3 times 10 to the minus 3. Please look. This gives me 3 times 10 to the minus 3. This gives me 1 times 10 to the minus 2. This is 0.25. There's a huge improvement, as you can see. By the way, I mean, let me say this fact. Whenever you are doing 3 precision point synthesis, if you change theta initial and phi initial several times, do trial and error, you may end up with a 5 precision point synthesis result. Or 4 precision point synthesis result, okay? I mean, depending on these angles, because K1, K2, K3 values that you have obtained is from the first three precision points, as you can see. This is a good way of performing synthesis, as you can see. Previously, it was Freudenstein, Levitsky, Seeker, who have determined this 5 precision point synthesis analytically. However, this numerical technique seems to be much simpler and much faster. And by the way, in case of 4 precision points, you will end up with 2 possible values for K1, K2, K3. If it exists, there are 2 solutions. Both of them can be imaginary, no solution. But if there's a solution, you are going to have 2 solutions. I mean, this is not a unique solution. You will end up with another solution if you start with a different initial condition. For 5 precision points, it turns out that you are going to have 3 solutions for K1, K2, K3. However, in all the problems that I have solved, I ended up with 1 solution. The other 2 turns out to be imaginary in most of my cases, but I cannot prove that. So there are 3 possible solutions, let me say. It converges to a single solution anytime I do it. Anytime, we'll be starting with any value that any initial theta initial and phi initial, I end up with the same result or no result. It diverges, the solution GRG diverges. And if you perform evolutionary, I have not used evolutionary method in these examples because it takes too much time. You can try evolutionary method as well. It is the computation times is more. As you can see, GRG is quite fast in these solutions. You can use the same method, the same concept for least square analysis, for mixed order synthesis, etc. But I'll keep it short. I hope I have not extended my time limit. So I will stop sharing and have good luck to everyone. And I'm going to end this session.